Why is the sky blue? It's probably one of the first big science questions we ever ask as kids, and the answer seems so simple, doesn't it? Well, what if I told you the answer we all learned in school is just the tip of the iceberg? We're going to dive in, because the real story involves the sun, our own eyes, and a hidden hero in our atmosphere that you probably never saw coming.
And hey, don't just take my word for it. Look at this. Researchers just last year, writing in a major science journal, basically said that the standard answer we all know isn't the whole truth. This quote right here, it perfectly sets the stage for the mystery we're about to unravel.
Okay, first things first, let's just bust the biggest myth right out of the gate. The sky is definitely not blue because it reflects the ocean. Nope, it's actually the other way around. The real story starts about 93 million miles away, with our sun.
Now, when sunlight hits your eyes, it just looks white. But that white light is a bit of a magic trick. Just like when you shine it through a prism, it's actually hiding all the colors of the rainbow, all bundled together. And each of those colors travels as a wave, but, and this is key, they all have different sizes or wavelengths.
Here's the best way to picture it. Red and orange light travel in these long, lazy, stretched-out waves, kind of relaxed. But blue and violet light, they're the opposite. They travel in short, choppy, high-energy waves. This single difference is the entire reason our sky has the color it does. So all this sunlight comes racing towards Earth, and bam, it slams into our atmosphere, which is full of trillions and trillions of tiny gas molecules. And this is where a process with a fancy name kicks in, Rayleigh scattering. All you need to know is this. It's a process that grabs those short, choppy light waves and throws them around way more than the long, lazy ones.
Let's just walk through it. 1. Sunlight enters the atmosphere. 2. It hits an air molecule. 3. That molecule acts like a tiny disco ball, but only for blue light, scattering it in every single direction. 4. Meanwhile, the red and orange light waves just cruise right on by. So when you look up, you're seeing all that scattered blue light coming at you from the whole sky.
And we are not talking about a small difference here. This effect is powerful. Blue light gets scattered about 16 times more than red light does. That incredible bias is what paints our entire daytime sky blue.
But hold on a minute. If you've been following along, a question should be popping into your head right now. If the shortest waves get scattered the most, and violet light has an even shorter wavelength than blue, then why isn't our sky violet? It's a great question, and it proves that scattering isn't the whole story. Well, the answer is this really cool mix of astronomy, chemistry, and our own biology. First, the sun just doesn't produce as much violet light as it does blue. Second, our upper atmosphere actually absorbs some of that violet light. And finally, and this is the kicker, our eyes are just built to be much more sensitive to blue light. So what we end up seeing is blue.
Okay, so this same science also explains the other most beautiful part of our sky. We figured out the blue part, but what about those incredible, fiery red and orange sunsets? It's the exact same science, just viewed from a totally different angle.
Think about it. When the sun is directly overhead at noon, its light is taking the shortest possible path to get to you. But when the sun is way down on the horizon, at sunrise or sunset, its light has to travel sideways through way more atmosphere to reach your eyes.
And because that light is traveling through so much more air, that scattering effect goes into total overdrive. By the time the light gets to you, pretty much all the blue light has been scattered away from your line of sight. So what's left? What's the only light that can make that long journey straight to you? The long waves. The beautiful reds, oranges, and yellows.
And you might be thinking, all right, I've got it. Blue sky, red sunsets. Case closed. But this is where the story takes a fascinating turn, because that is not the whole story. In fact, for a key part of the day, scattering is actually the sidekick, not the main hero.
So here's the real puzzle. Picture a sunset. The sun on the horizon is a blazing red. But if you look straight up to what astronomers call the zenith, the sky is often this incredibly deep, pure blue. How is that possible? If the long path scattered all the blue light away to make the sunset red, how can the sky above you be so blue?
A scientist named Edward Hulbert obsessed over this, and what he discovered was just stunning. He calculated that for the sky directly overhead at sunset, a full 2/3 of that blue color has absolutely nothing to do with scattering. There's something else going on.
And here it is. The hidden hero of the twilight sky is ozone. Yeah, the ozone layer. We all know it absorbs UV light, but it turns out it also absorbs yellow and orange light. So at sunset, it acts like this amazing filter, literally eating up those other colors and letting the pure blue light shine straight down on us. So let's put it all together. That deep, beautiful twilight blue is a team effort. Our old friend Rayleigh scattering is doing about a third of the work. But ozone absorption is the real MVP, responsible for the other 2/3. That is the complete and frankly much cooler story of our blue sky.
And it keeps going. You ever wonder why on hazy or humid days the sky looks kind of pale or whitish? Well, that's because the air is full of bigger things, like water droplets or dust. They cause a different kind of scattering called me scattering, which scatters all the colors pretty much equally. And when you mix all the colors, you get white.
But here's maybe the most mind-blowing fact of all. Our sky wasn't always blue. For more than half of Earth's history, the sky was probably a hazy orange, thanks to an atmosphere full of methane. It was only when tiny little microbes started pumping out oxygen that our atmosphere and our sky slowly transformed into the blue world we know today.
And of course, every planet is different. Take a trip to Mars, and during the day, you'd look up at a reddish, butterscotch-colored sky because of all the iron dust. But get this, at sunsets, the sky around the sun on Mars glows blue. It's the total opposite of our sunsets.
Which leaves us with a final, really profound thought. Our blue sky is a direct consequence of an oxygen-rich atmosphere. And that atmosphere was created by life. So as we start looking at planets orbiting other stars, if we ever find one with a sky that looks just like ours, could that be a sign that we're not alone? It's something to think about the next time you just look up.